The recording is started. So let's begin. So thank you everyone for being here or on Zoom today for the talk from David Whitworth. And let me introduce David. David got his PhD from University of Manchester in 2022, working with Dr. Rowan Smith. Then he spent 1 year as a postdoctoral researcher at Heidelberg University. And now he is a postdoctoral fellow at UNAM, working on understanding molecular clouds and star formation through galactic scale simulations. So today we're going to hear him talking about magnetic fields in the multi-phase ISM and CO dark star formation. So David, the floor is yours.
Thank you. Thank you very much. Sorry I couldn't be there in person. I had hoped to be there, but travel budgets being what they are, I've been unable to make it over. So yeah, I'm going to talk today about mostly magnetic fields, and then a recent paper I just put up last week onto arXiv. So the abstract is slightly different to what is advertised, but it's mostly still the same. So yes, I'm currently here in Mexico, in the wonderful town of Morelia, see these wonderful pictures here. It's not always that sunny. Today is quite cloudy, so it's not always beautiful weather here in Mexico. All the work we're talking about has got all of these wonderful collaborators on here from all over the world. So let's dive straight into magnetic fields. If my slides work, there we go. So magnetic fields is always everyone's favorite question. Whenever you go to a conference and no one knows what to ask, someone will always ask, what about magnetic fields? Luckily, we are now starting to understand them a lot better. And it's an easier question for the person up front to answer than it used to be. But they exist everywhere in the universe. We've got planets to stars, cores, filaments. We get these amazing pictures from aurora that happen. And then from there, they go up to giant molecular clouds. We get supernova issues, galaxies with the large-scale dynamo clusters and beyond. So magnetic fields are ubiquitous. We find them everywhere. So it's important that we understand them and where they come from and how they affect galaxy evolution, star formation, and the like. So where do they actually come from? How do these magnetic fields arrive in the universe? Well, the answer is we don't know. So cosmologically, we don't know where they come from. So this is a major question that I know a lot of people are looking at, and it would be great if anybody has any answers. But one possible method for the astrophysical idea, so what we see in the modern universe, is what's known as the Biermann battery. And this is just your basic physics. Electrons move around in circles and we get magnetic fields. So because they're moving around, we get this field, but the field is very, very weak. It doesn't like to grow above about 10 to the minus 12 microgauss at most. So we need ways to strengthen the field for the ones which we view. And there's a couple of ways we do this. The first one is the small scale dynamo. This allows a weak field to grow. We see this in the ISM through this wonderful circular movement of the field lines, which then stretch, they twist, they fold, they merge, and it kind of goes around in this cycle. It's a small-scale dynamo driven by turbulence. So a supernova can go off, it will bend the field lines, and we'll get all of this stuff happening. And it tends to work on very, very small scales, hence the name small-scale dynamo, of usually less than a parsec. And they take tens to hundreds of mega years to reach kind of the maximum level that can be supported by this mechanism. They cannot generate the high field strengths that we see in the Milky Way. So we can see, on average, the Milky Way is between 6 to 10 microgauss, with the regions up to a couple of 100 microgauss around magnetars. So how can that happen? That happens through the large-scale dynamo. And this is driven by the galactic rotation in shear. So the actual galaxy rotating drives the growth of the magnetic field. And this allows us to get to these higher field strengths. And it has a lot of effect on the morphology of a galaxy, as we'll maybe see in some pictures later. And it saturates after a couple of gigayears. Now, the timescales here are important when I come to talking about simulations. So small-scale dynamo is on the region of a couple of 100 mega years. Large-scale dynamo is on a couple of giga years, usually around 3 giga years. I'm not an observer, but I'm going to give you a very brief summary of what I know about observing magnetic fields. If anybody knows any better, please tell me where I've gone wrong. But the most common way we observe them is with Zeeman splitting. Well, I wouldn't say the most common. One of the most preferable ways would be with Zeeman splitting, which is the distance between sublevels in the magnetic field. And we can view it through H1 emission, OH and H1 absorption, CN, and these things. And these all trace different density regimes of the magnetic field. It's a line-weighted intensity. However, it is line of sight. So it's only one direction in this 3D structure that is the magnetic field. And it's based on the Stokes V spectrum with this equation. The most common, this is the most common, not Zeeman, this is the most common, the Davis-Chandrasekhar-Fermi, DCF. And this comes with a lot of assumptions. It assumes that the underlying magnetic field is uniform and is connected to the turbulent motions in the gas. Its dispersion in polarization angle is produced by propagation of only the incompressible MHD modes, and that the gas is fully turbulent and all energy is transferred to magnetic energy fluctuations. And these are quite big assumptions. And it relates the density of the gas, its velocity dispersion and polarization angle to a plane of sky, so a 2D version of the magnetic field strength. As I said, it also makes other assumptions. It assumes that turbulent is subalphenic. It does not take the compressible mode, as I said. And the underlying magnetic field geometry is linear. So with all these, it very likely overestimates your magnetic field strength due to error in propagation. And Kate Patel, in her 2022 paper, The Protostars and Planets Review, estimates it at around 6.3 times higher than the Zeeman. And you can see this in the plot, and we'll come to these plots later. The red line is the Zeeman data, and then the yellow line in the other plot is the DCF average. And you can see how much that's shifted up. There are other methods. So there's a new version of the DCF called the Skalidis and Tassis method. And this does take into account compressible modes. This is still being looked at as to how viable this is. We have Faraday rotation. And I know this is being discussed again with things like the SKA. So they're looking at that again. We have the velocity gradient method from Alex Lazarian, very complicated method. And then we've got some dust extinction and emission polarizations as well. So there's multiple ways we can view it. And we're all very sad that Sophia is no longer around to help us. I know Shuo will probably have some opinions on that one. So why are magnetic fields important for star formation? So it's been shown throughout kind of recently that they have this different effect. So this is all galactic scale and cloud scale stuff. So the field strength affects our star formation rate. So I show that the star formation rate may not affect the magnetic field may not affect a global star formation rate. So that's the plot on the left. But other work has shown that depending upon the field strength, it can affect the star formation rate, which is the plot on the right from Hector Robinson's work earlier this year. And so there's also this idea in cloud scale stuff from Patrick Enabel and Mark Krumholtz that it suppresses or delays star formation. And so there's still a lot of conversation going on as to kind of how this all happens and what goes on with it. Because we also see that it's likely to generate more molecular gas mass. And this is obviously important if we consider stars to form in cold, dense molecular gas. And so in my work and work from Philip Gildes, we see more molecular gas mass arise, but the actual dense gas within the models doesn't increase. And this is likely to do with the support from magnetic fields. I'm currently looking more into that at the moment, so expect work on that within a year or so, maybe. Observationally, it's been shown that it suppresses core fragmentation. This work by Einar Palau in 21. And because of this, it's likely to reduce the number of cores and clumps we find. At larger scales, we expect gravity to dominate, but the field may still be important. So there's various ideas, depending upon your field strength, depending upon the gas density and things, it's likely to have some effect, but gravity may well be stronger. And there's work here by Ryan McGuinness, who was a master student of Rowan's. We're currently working on the paper. I think those pie charts have actually changed in the last week, so ignore those. But moving on to some work I've actually working on the referee report on now. So is there a relationship between the ISM and magnetic fields? Well, yes, to some extent. At larger scales, it might dominate over gravity, it might not. Cloud and core scales, magnetic fields are definitely important. And at stellar core and smaller, gravity definitely dominates. So we've got this multi-scale influence happening. And we see that in this wonderful plot from Dick Crutcher in 2010. This is quite a famous plot and famous relationship, where he did a Bayesian analysis of 137 Zeeman measurements and found that there is a relationship above 300 centimeters cubed, that it kind of grows by about 2/3. There is little work that has been done on it since then. Jiang et al. In 2020 showed that the slope varies depending upon how you introduce your priors and error analysis in this. But one thing they did here, which was similar to what Richard Crutcher did, is they keep anything below 300 as flat. They assume no relationship, so they don't assume any relationship in the diffuse gas, which I will come to in a bit. See, as I say, they don't look at this part, and they claim that there's just not enough data here to fully analyze it. But the diffuse region is dynamically and kinematically important to cloud growth. Your gas in your cloud comes from this region. And if there is a strong magnetic field here, it is going to slow down the accretion of this gas onto your cloud. So we need to look at this in more detail. So can we do this? Can we actually look at this? If we look at this Patel 22 paper, Kate collected 700 DCF measurements from 24 years of data. And this includes really diffuse 10 to the minus 2 gas. And it also goes up to 10 to the 9, so dense stellar cores. So can we actually use this data then to improve our fits? And so this is what I have been doing. But there's a lot of caveats, as always, on this. Not all of the DCF data has errors on it. As I said before, it likely overpredicts. DCF is plane of sky, Zeeman is line of sight. So there are some scale factors we can use to kind of try to match them, but a true comparison comes with a lot of caveats. So we do a new analysis. We submitted a paper, we submitted this and it's on archive, but we're working through the referee report now. So we find the mean posterior of 5 free parameters, which are listed there. We have the number density, magnetic field strength, the exponent in the diffuse gas and the exponent in the dense gas, and log V, which is a nuisance factor, which basically states we don't trust our errors. In the new, we're doing a new version where we're also adding in an extra parameter, but I'll come to that in a minute. And we're modeling this as a two-part power law, where we allow that diffuse slope to vary, unlike the original work, which kept it flat. So we tested various priors for this. This is a little bit of statistics, so I do apologize to everybody. Priors are basically your initial range of values you think it could lie within. So we initially started with what we called a flat unconstrained prior. We kept it very, very wide. It was just basically a top hat function. And we got this horrendous looking corner plot. The data is just all over the place. What you're looking for here is kind of like nice Gaussian blobs in the center of the squares. And we're just not seeing that here. So we then constrained these parameters a little bit, but we got something similar, so it didn't really work. And then we moved on to a Gaussian prior. And this came out really quite nice. There are reasons why this is nice, and this is a lot to do with my lack of understanding of Bayesian analysis, but it looks quite well constrained. So we looked at that and we plotted it. We scaled both the Zeeman and the DCF data to be 3D and in line with each other, and we get this relationship. So we have this new two-part one where we have a slope in the diffuse gas of around 0.27 and one in the dense gas of about 0.54. So we are seeing this connection where the diffuse gas does have a slope within it. And you can even look at the spread of data in this plot and see that it is kind of more or less where you'd expect it if you just did an by eye fit. So we then got the referee report, and we didn't include any errors in the B field because the errors in B field are dependent upon many things and untrustworthy. So the referee asked us to do this, and we're doing it now. So we are doing this with the DCF data at the moment, and we've added in, you'll see at the bottom, this other prior term called rho. And this is basically saying how much we trust the correlation between the B field errors and the number density errors, because the equation connects the two. This is very much a work in progress still, but even still with a work in progress and just using a flat unconstrained prior, we get a pretty good fit. Apart from the bottom row, row still needs a bit of tweaking, but the other results seem quite well constrained. If you look at it, you might have some questions. The bend seems quite high. There are reasons we could have it that high, and it relates to the Alfvénic Mach number, kind of highly theoretical reasons, but we're still working on it, but it's certainly nearly there and quite well constrained. So we're still seeing that diffuse slope. But what drives the relationship? So there's been a lot of thought as to why the original relationship was turned over at 300 centimeters cubed, and most people say that's about when gravity kicks in, when dense gas is considered formed, and when we get giant molecular clouds. But it's kind of hard to determine from observations specifics as to what is happening. And so can we use numerical simulations then to help us understand what drives it? And the answer is yes. So the simulations allow us to test various processes. So we can look at galactic rotation, so shear, so the large scale dynamo. We can look at supernova, how that affects the diffuse gas. We can look at resolution, because we know the small scale dynamo acts on very small scales. And we can also look at the time growth on this. So when I started this, I just had my model, and then people started giving me their data. I now have 19 different simulations from 4 different codes across scales, from protoplanetary disks all the way up to Milky Way galaxy scales. And we have this massive density range of 10 to the minus 6 to 10 to the 13. The quick answer is it really depends on what model you're looking at as to what your relationship is. So you can see all of the models on that table and all the different data. We won't go through the table in detail, but we'll go through some of the models so you can see what the plots look like. So if we take a small turbulent box, so we've got two here. One is 500 parsec box and one is a kiloparsec box. And these don't have galactic rotation. They don't have shear. So these are just cloud scale simulations in boxes, in turbulent boxes. These don't show your traditional relationship. They're not representative of either the original, I've removed this slide, sorry, the kinematic or dynamic relationship. So in 1976, there was a paper where the original slopes came up. One was 0.5 and one was 0.66, depending upon how the gas collapsed. And we don't see that at all in these turbulent boxes. And so, well, we've got turbulence, we've got star formation, we've got supernova. Why do we not see this relationship arise? Well, let's look at a larger scale simulation. Here we have two Milky Way scale, well, one Milky Way scale simulation and my dwarf galaxy simulations, where we have rotation and we have a long period of time for the magnetic field to evolve. And we begin to see this relationship arise. So we have a continuous slope. We have bends in various places, which is dependent a little bit on resolution. But it's kind of what we'd expect. Then if we go even more resolved, so and look into kind of the evolution, the changes, how it happened, we don't see that much difference on a Milky Way scale or in a dwarf galaxy scale. It gets better because we have more points in the data to pull from, but there's not that much change in the relationship. But we have the slope. We have between 0.5 and 0.7, depending upon the model. But how does it arise still? So we know now, we've shown here in these two slides that it's likely to be a galaxy relationship. So we're not seeing it in the clouds, but when we look at galaxies, we start to see this relationship turn up. But is it driven then by turbulence? Is it driven by shear? Is it what actually drives it? So we have these models from Frederick Gent, who is looking at the small scale dynamo and the large scale dynamo effects. So he ran two pencil models. These don't have gravity. They don't have self-gravity in it. They're pure turbulent driven models. And as the small scale dynamo is driven in hot turbulent diffuse gas, we do start to see this relationship arise. So we have star formation here and we have turbulence here, but we don't have gravity. So it's not necessarily driven by gravity, but it is definitely driven by turbulence. And so observationally, we see this fit as shown earlier. And then the numerical simulations help us determine the processes that lead to it. It takes time. So you do need to run your simulations for time for the field to fully saturate and become active in all parts of your diffuse gas. Resolving the gas is important to some extent because it then allows us to resolve the SSD, which will allow your magnetic field to increase quickly. It's driven by turbulence, shear, supernova, rotation, and it's a galactic scale relationship. The simulations that match best to the observational results are the galactic scale simulations. So if you go off and you observe a small region, you may or may not pull out the relationship. But if you take an average over multiple regions, that's when you start to see the relationship arise. So that's the MHD stuff. It's quite exciting. As I say, we are working on the referee report and hope to have it back before Christmas. So expect hopefully a new version soon. But moving on from there, a paper I've just submitted. This is on CO dark star formation. This is the last project from my PhD. It's taken some time to get published for various reasons, but it's now on the archive. So why is this important? Why CO dark? So stars are expected to form, as we know, in cold, dense molecular gas. However, there has been work that has shown at low metallicity, this might not be true. So the work of Glover and Clark in 2012 connected it to H1 cooling and just dense atomic gas rather than molecular. Whilst when we go up to higher metallicity, so say 10% of solar or higher, the gas is more likely to be molecular. And this is work shown by Hu et al. 23, 22 and things. So how true is this? I thought I'd try this. So I took my models from my 22 paper. These are hydrodynamical models. They don't include magnetic fields. We include supernova, photoionization, and a time-dependent non-equilibrium chemistry. These are the highest resolution, not just dwarf galaxies, but galaxies ever run. We get down to stellar core resolution in the densest gas. So we're at maybe 2000 AU around our our particles. So insane resolution for a galaxy model. They did take some time to run. But so we have these, and this allows us, because they're so low metallicity, to fully resolve the CO. We looked at this, and we looked at, on the left-hand side, we've got the 4 models. We've got the surface density of CO plotted over the H2 molecular gas. And well, you can't really see much CO in there. There's little bits you can probably see in the bottom, what is that, bottom left corner, Z10GO1. You can see a little bit of the red and yellow poking through, but it's really not much. So for visualization, we smooth it out and you can actually see there is some CO there. But if you look at the scaling, it's really quite low. There's just not much here at all. And so to work out whether we can actually view this observationally, we took clouds from this based on density cuts, looking at the CO. So we took CO density cuts, and then we ran them through an RT code called Polaris, and we come up with the 12 COJ to 1, J1 to 0, 1 to 0 emission. And these are the plots that came out. So there's 48 clouds across all 4 models with varying integrated emission. We looked very briefly at the conversion factor, and it's highly variable. This XCO conversion factor is highly, highly variable, really dependent upon multiple things. It's in agreement with some observational and theoretical work as well. So be careful when you look at XCO factors. These are based upon only the regions. We don't look at the whole galaxy because there's so little CO in the whole galaxy. We can't really run this on the whole galaxy. But we then smooth them with 2 beam sizes based upon ALMA, 2 different baselines on ALMA, and we see whether ALMA can see these things. It's mostly CO dark, except when we go to the highest resolution, 1.5 arc seconds, depending upon what type of galaxy you're looking at or where you're looking at in a galaxy. You might see it, you might not. So they are quite CO dark. But so if we've got CO dark, does that mean we don't have molecular gas? Are stars then forming in atomic gas as predicted? So what I do to have a look at this is I find all of my sync particles. Here we have sync particles representing our stars. These are accreting sync particles, not just stochastic. And we draw a 3 parsec cubed box around each sync particle and look at the gas contained within it. We have volume weighted and mass weighted here. and we plot the number density against the age of the sink. And we can see that, yes, these sinks or star-forming regions are existing within dense molecular gas. We do volume weighting and mass weighted because a repo is a little bit weird, as Shiro probably knows. And it's an amorphous cell, it's an amorphous grid. The mass weighting shows that most of the mass exists in very, very small dense regions. And the volume weighting shows that kind of a more average cloud-like view. So, but we can see here that, yeah, the sinks are existing in quite high density regions, even up to maybe 8 mega years. We get sinks in quite 8 mega year old sinks. We get them in dense gas. This is just the same plot, but with the mass of the sink rather than the age of the sink. And then this is the same thing with a really bad copy of the table. There's a table. So we looked at the fraction of the sinks as they existed in different regimes of the gas. And most sinks exist in dense gas, especially when they are young. So they form in the dense gas and then they drift away or move away due to various processes, whether that's just natural drift or the cloud is destroyed by turbulence. And so, sorry, this has been very, very brief. The sink particles form in these small, less than 3 parsec cube cold dense regions. They can decouple from the gas, usually after about 2 mega years. Older sinks still exist. I seem to have missed a table of this. I thought I had another table that helped with this one. The regions surrounding the sink are less massive, and mass loss is driven by feedback. And low metallicity dwarf galaxies are either fully dark or have high dark gas fractions, depending on beam size. So they would be difficult to observe with ALMA. And so we'd probably need other proxies, so maybe dust to view them. I do have someone here who in UNAM, Roberto Galvin, who is taking this data and is going to run it through an equivalent single dish or maybe NVGLA-like observation to see whether that changes things. So kind of looking at deep field observations rather than what I've done here. So there's going to be more work on this soon. And so brief summary, there is a diffuse slope in the B rho relationship, and stars, even at low metallicity, do initially form in cold dense molecular gas. And I think that's it. That's all I've got for today. So any questions? Sorry, that was a bit quick. I got my times confused. I thought I was at the same time zone as Arizona, but I'm not. I'm an hour ahead of you, so I do apologize.
Okay, thank you, David. Any questions in the room or online? So I have a question about the B-bro relation. There was one simulation where you didn't include self-gravity, but you still see the braking part.
Mm-hmm.
So does that imply that you don't that braking part that Crutcher's saw doesn't necessarily mean it's due to gravity?
So yeah, so the original relationship 2010 doesn't state a reason why it appears there, but a lot of people have assumed that that's because it's where we all expect clouds to that the dense gas to start collapsing and we get our giant molecular clouds. There is theoretical work. So there's a paper that Enrique always likes to go on about to me from 2003 from himself and Tasso. And then there's more modern work from a Chinese group, I forget who, that show that the actual break in the slope appears depending upon the alphenic Mach number in the gas. So it's a lot more related to how the alphenic waves are behaving. And it can go from anywhere from where we see it up to 10 to the 9, 10 to the 12 number density. So it's highly variable from theory. And we kind of see that a little bit in the DCF data. So as I say here we've got this really, really high bend appearing. So I think moving forward from where we are with this work, there needs to be kind of a better analysis, a more focus on why and where this break occurs. So in the self-gravity model without self-gravity, sorry, my video was over the top of it. We have the kind of a downward trend in the dense gas at the beginning, and then it starts to kind of rise. And this is what is predicted by the theory with alphenic Mach numbers as well. So it's a lot more to do with, rather than gravity, but the turbulence that is arisen. But yeah, I think that there needs to be a lot more detailed work done on this. So this paper is kind of a, what's the word? An overview of the state of our knowledge at the moment. And I have a lot more projects based on this. So I'm hoping in the future that we can tie it down better.
And was it the Huabai Li's group you were mentioning? I think they did study the Crutcher relation relations, and I forgot exactly what their conclusions were.
No, I think that's he went to Germany, didn't he? He was at the castle.
Yeah.
Yeah. No, they're looking at cores and the evolution of the relationship with dense cores. So they're looking at individual objects and their evolution, where they kind of lie throughout their evolution on the slope. If I could get I can't remember the name of the other group, but it wasn't them, but I do know their work. So yeah, they were also related to where is it? This group. It's kind of the same group. So
yeah. Okay, thank you. Any other questions?
Yeah, you said you put in galactic, it was important that you take into account the galactic motions.
Yes.
But what exactly does that mean? You put in an axisymmetric shear, or is there full non-axial symmetry?
So where are the plots? So the thought is within these turbulent boxes. So it's not so much. It is kind of like the galactic. It's more that it's a galactic scale relationship. And if you want to do a galactic scale relationship, you need to account for the movements of the gas within the galaxy. So these models, these turbulent boxes, don't have rotation in them. They're purely driven by, I think, I can't remember what they did, but one of them is a sinusoidal version. I'm not too au fait with how people put turbulence into boxes because I do galaxy simulations, but these are just boxes, cloud collapse. The galaxy models obviously are just naturally driven through their potential. And these models, I can't remember how Fred did this, but he does have, so they're pencil models. They're like taking a a long, thin view through the Milky Way disk. So he does have a shear component to his models. One thing that it could be is a time-dependent thing. So if you look the Frederick Gens models here, these run for 3.5 gigayears, and that's when we start to see it. So the box models here may not have run for long enough for it to arise. So it could be a galaxy thing, it could be a time thing, and trying to convince somebody who does box models to run their models for a couple of hundred mega years, let alone giga years, is not going to happen.
There was a paper a few years back by Royals and Latta, which looked into the effect of spirals on the dynamo. Is that what is your opinion of work like that? Is that useful, or is that a side issue?
For me, any work on magnetic fields is useful. But it kind of, for this current work at the moment, it's probably not too useful for me. But going forward, then there does need to be more work on it. But it also kind of depends on who you ask. So I'm very much in support of looking at the effects of the small scale dynamo and large scale dynamo, and how they actually behave, because this is how the magnetic field grows within a galaxy. But people just kind of accept that. Like I work quite closely with Enrique Vasquez Semendai here. He's my boss, and he hates the small scale dynamo and large scale dynamo models. He's very much more on talking about fast and slow modes. So it kind of depends on who you ask. Observers and people like me who do galaxy scale simulations, we like it, but more numerical theory people prefer talking about other ways. So I'm trying to kind of bring the two groups together with this.
Hi, I have a question about what you said at the beginning of the talk when you were explaining why magnetic field is important for star formation. It's not my field. I usually silently ignore magnetic fields, so please bear with me.
That's okay.
You said that the magnetic field can regulate the mass or molecular mass, something like that.
Yeah.
Could you elaborate a little bit more on that point? What mass do you mean? It's the mass of the core, mass of the clamp. Where is this mass coming from?
So this is actually something that I've got like 700 projects going on at the moment as a result of all of this. So it's this plot here on the left. This is a comparison plot between some magnetic field models. So the magnetic field models are in the solid lines, and hydrodynamical models in the dashed and dotted lines. These are dwarf galaxy simulations, so it's a galaxy scale stuff. And this is just cumulative mass of H2 within the disk. So it's not separated between clouds, cores, clumps, diffuse. This is just the total cumulative versus density. And so in the magnetic field models, we see over time more mass of H2 in dense gas. So if you just take the, can I see draw on the screen here? This would be good. If you take the 1 gigayear, so fully time evolution, and you look at 100 number density of 100, we can see that a lot of the mass does sit in the dense region, and it's a factor of a couple more than in the hydrodynamical case. We have some projects moving forward to see why this is a thing. and why this doesn't actually affect the star formation rate. Because you would expect if you have more molecular gas, the star formation rate would increase. But what we see is it doesn't actually change. So bear with me. The answers will come at some point, I think.
Okay, thank you. Thank you very much.
Any other questions? So if not, we thank David again, and thank you all for coming to the meeting today. We stop recording.